so I'll give, my short answer to this is probably being afraid is not helpful, although I definitely think there are many things that it's valid to have fears for, and it's going to be up to us to figure out how to make AI useful and to keep making humans useful in light of AI. And that's going to be a big challenge. It's going to be a challenge for your generation. But AI is just a tool, right? It can be used to do harmful things. It can be used for good. This is the only AI-generated image I'll use in the talk, although there's always a temptation to use AI tools to generate images, and they can do a lot getting at the question of sort of roles for humans. They can certainly do a better job than I can. Like a trained artist and illustrator might do better than that, but the AI tools do pretty well. And AI is a tool, so it can be used for both good and evil, but it's very different from any other tool humans have developed and have access to. So there's, and I'll get into why it's different and what's different about it, but that's something that poses high risks if we don't manage it well. So the plan for the talk, so I will answer this question. There is not a generally accepted definition for what is artificial intelligence, right? So when we ask a question like, should we be afraid of AI, we got to figure out what we're talking about. There's lots of effort in governments around the world trying to figure out how to regulate AI. Most of those regulations don't have a clear idea of what it is they're actually trying to regulate, what AI is. So I'm going to try to give a definition that's precise and get into how machine learning works, which is often what we mean when we say AI these days, and talk a little bit specifically about how ChatGPT works. How many of you have used ChatGPT or a similar tool? Okay, almost everyone. Okay, good. And I guess I won't ask, well, maybe I will ask later. We'll leave it for the discussion later, what your schools allow you to use it for or don't allow you to use it for, and if you have rules about when and how you're allowed to use these tools. But then we'll get into possible harms. But definitely feel free to interrupt with questions. If I don't get through everything, that's fine. I know that we're a little delayed. I think one school is still on the way, and do want to make it as interactive as possible. And I should mention, I do have a few door prizes, which I can give to people. So the first answer to my why you're afraid of question, I hope I remember, who was the first one to answer it? Over here, yeah. You get the first door prize. I have a few more, but this is my children's book on theoretical computer science. So if you haven't had a computer science course, hopefully it will be valuable. Okay, so what is artificial intelligence? So there are lots of different definitions out there. This is a common one, is AI is about making computers that do better than humans at cognitive tasks and maybe do better than humans at all cognitive tasks. Like that's sort of this vision for what's sometimes called strong AI or general AI or artificial general intelligence. And if we're going to define AI in terms of doing as well as humans in things, we got to figure out what are the things that we decide are the cognitive tasks we care about, right? Because if our cognitive tasks were, say, adding numbers and doing arithmetic, computers have been better at humans at that for many, many years, right? If our cognitive task is playing games, well, maybe some of them computers are better than humans. This is, if we looked about 10 years ago, which ones humans are better at and which ones computers are better at. So welcome. Glad you found the way. So we're just getting started. Yeah, we'll let the new class come in. There, good. All right, so welcome. Thanks for joining. And so we're talking about sort of what artificial intelligence is. And some definitions of it talk about, well, it's getting machines to do things humans can do as well as humans. And if we looked about 10 years ago, these example tasks, some are ones that machines can do better, some are ones that humans can do better. Over the past 10 years, a lot of those tasks have transitioned to now machines do them better than humans. Right? But it depends a lot, and the ones that are kind of blue check marks, it's sort of fuzzy whether the human or the machine does better. I do not speak Arabic, so I asked for the text and image to be translated, because if I was going to put it on my title slide, I wanted to know what it said. I think it did a pretty good translation. Those of you who speak both Arabic and English better than me might say, a professional translator would have maybe picked some words a little differently or done things in a more poetic way, but got the basic gist of it pretty well. So if we're going to look at specific cognitive tasks and whether machines do them better than humans, we can look at what the very best human alive today can do, or we can look at what typical humans that are good at those tasks can do. And for some tasks, like adding numbers, well, machines have been better than humans for 400 years. For other tasks, machines got as good as a typical human and then maybe took a little longer to get better than the best human. And then there's some tasks like making up jokes or translating language that machines are better than almost everyone, including people that have been trained in the languages. But the very best human translators will do better than machines. And the one I've got on the bottom, the things that we think of as high-level cognitive tasks, like playing chess used to be an example of this is the goal of AI, have proven to be much easier for machines than things that we think of as not really hard cognitive tasks, like folding clothes, right? Manipulating objects in the physical world is still something machines struggle at, but are getting better at. Okay, so I don't like that definition, right? So any definition that's based on cognitive tasks that's both very imprecise. We've got to decide which cognitive task and how we measure how good humans are and how we compare that to machines. It's very sort of centered around human biases and human abilities. And it's very limited in ambition, right? There's no reason we should stop expecting machines to get better once they get as good as humans. So I want a definition that has more ambition as well as more clarity on what AI is. So this is a quote that is not talking about AI. It's talking about computing in general. The human race will have a new kind of instrument which will increase the power of the mind much more than optical lenses strengthen the eyes, and which will be as far superior to microscopes and telescopes as reason is superior to sight. Any guesses who said this or when? And I do have another door prize for a good answer, or at least a bold guess on this. So yes. Elon Musk. Oh, that is an interesting guess. It is not Elon Musk. But I will quote Elon Musk a little later today. So you get partial credit for Elon Musk. Yeah. Steve Jobs. Okay, so we're thinking of people building computers. Steve Jobs has a great quote about computing being like a bicycle for the mind that kind of touches on this. This was actually much earlier than either of those. So. Einstein before he died. Not Einstein, yeah. And I don't. Einstein definitely was involved indirectly in computing because of use of computing in physics, but was very not known to be involved in computing in any direct way and was much more of a theoretician. So, but before Einstein, even earlier. Bill Gates. All right, so this is another sort of industrial computer scientist. Did a lot to build software, but didn't have a vision like this. Yeah. Charles Babbage. Okay, good. So now we're getting earlier. This was actually, so Charles Babbage was in the 1830s building the first computing machines that aimed to be general purpose computers. This is actually much before Babbage even, right? So, but I will give you a door prize because that's the closest to being on the right track. This is actually Leibniz in the 1670s. So maybe you can hand that. Yeah, thank you. Okay, so it goes back, 400 years or so, thinking about the power of computing. And I really like the quote because it's talking about amplifying human intelligence, right? This is about amplifying the power of the mind. And that's what computers do, right? So computers are really information processing devices. They take input in the form of bits, any way of encoding information. They do some processing and they produce output, right? And those inputs and outputs might be connected to sensors in the physical world, but the computing part that we think about as computer scientists, at least, is mostly just the information processing. And part of the input going in is a program, right? This is a program. We think of these as being created by humans to tell the computer what to do. Right? This is how we get the computer to perform the computation we want. And this was really Leibniz's vision. And from the 1670s through sort of the first computers that could actually compute in a useful way in the 1940s to what I'm guessing, if you're like American high schoolers, you all have in your pockets like that. Do you all have smartphones? Is that true? I think people have smartphones all around the world today, right? These things have become very powerful. And with this vision of automation and what computers can do, we're able to, anything that humans understand well enough to describe with a program, with a sequence of clear, precise steps, well, now we can do it quadrillions of times faster than humans can do it. I know one of the early responses was, oh, machines are always going to be faster than us, right? Machines can do operations, once they're defined, much faster than humans can. And not just what any one human understands to do, we can combine the knowledge of all the humans working together, storing data, working together to write programs. It enabled millions of humans to work together as well to come up with those programs, right? So certainly this has matched the vision of we can amplify the human mind. What AI does is different from that. It goes beyond what any humans can do, right? And the difference in AI is all of this automation that was envisioned back in the 1600s and that we've built up until today depends on humans designing and programming the rules, right? It's following instructions in the form of a program that humans created. Whereas what we get with AI, which is often synonymous with machine learning, these terms used to mean very different things. Today, they kind of mean the same thing, right? And what is happening with AI and machine learning is now, instead of humans writing instructions and machines following them, the machines are being trained. Right? They're being trained through a training process that humans designed and wrote instructions how to follow, but the machine is now being trained based on data to do something that humans don't know how to describe. It couldn't explain what the steps are. Sometimes they're tasks that humans are good at and are able to do, like recognizing people's faces or understanding language. But sometimes it's tasks that humans don't know how to do, but they're all tasks that we don't know how to describe how to do. So that's what machine learning is. So I'm going to give a very quick introduction to understand the basics of how machine learning works and what it is. And the goal of machine learning is always to, instead of programming a machine manually with instructions humans know, to train a machine to solve some problem we don't know how to do. So some machine learning is supervised. What supervised machine learning means is we're starting with training data that gives what we want the answer to be. So we can imagine each of these data points, and they're labeled as blue or green. And what we want to do is train the machine to give us those labels for new points and learn that pattern, right? So that's supervised machine learning. In this case, we might say, well, this is a pretty simple problem. We're going to assume that there's a line that divides the green and the blue regions. And what we need to do is learn that line. So the line can be represented by a function like this. And to learn it, we're going to need to guess those parameters, right? So we might start with a guess that it's a straight line, and that doesn't work very well. We're going to measure the error, which points are correct, which points are wrong. And if too many are wrong, we're going to make another guess. And if the number that are wrong increases, well, that was a bad direction to go. We're going to go in the other direction, right? And we're going to keep making guesses until we get to a low error rate, which in this case, we can actually get to an error rate of 0, which is unusual. And then we've learned those parameters, right? And it only required guessing and maybe a little bit, if we're going to get there quickly, making sure we go in the right direction. For more complex problems, well, it's not going to be a line that distinguishes the regions that we want. We're going to need a more complex function. So it's going to have more parameters to learn. But the idea is the same. We're going to start with a guess, and we're going to keep adjusting things until it gets better and hope that we go in the right direction. And if we're talking about things like classifying images or more complex settings, we've got high-dimensional input. We've got a whole image of data. This is just one slice of that region, and we're going to find some region that corresponds to these are dogs, right? And those kinds of classifiers can work really well, right? To train a model in that kind of setting, well, we need a function with a lot of parameters, right? So we need a function that can represent lots of different functions based on what we learned, based on our guesses, based on following training. And pretty much all machine learning works like this. And for those of you not used to reading code, hopefully this still makes sense. But basically, we're going to start with a random guess, and then we're going to keep going until we get to something we're happy with, or we run out of money or time and have to give up. And each step, we're going to adjust those parameters, and we see if it gets better. And if we're lucky, we're going to adjust them in the right direction until we get something good. What we need is a function that is powerful enough to represent the complexity of the thing that we're trying to do. And what should that function be? Well, the best learning devices we know of are our brains, right? They're still better at learning than anything else. So this has been the inspiration that led to artificial neural networks. So biological neural network, we have about 100 billion neurons in our brain. Each neuron is connected to about 1,000 others, so that means we have 100 trillion connections. And that all, in some complicated biological processes we don't have much understanding of, enables us to learn. Right? We're making new connections, we're changing how the neurons are connected, and there's lots of mystery about how this actually works, but it's an amazingly efficient learning machine. Your brain uses about 25 watts of energy when you're awake, more if you're thinking hard, less if you're asleep, but much less than my laptop is using. Right. And the model that's used in machine learning of a neural network is a very simple artificial version of this, to say all the things that are connected to this neuron we're going to add up. We're going to multiply each one by some learned parameter. So this is how we have the ability to learn. And then we're going to take some function of those. And the one thing that's a little bit necessary to be able to learn complex functions is we have to have a nonlinear function. So the simplest one is just to say, if the value is below 0, the output is 0, and otherwise the value increases with the value of input. Right? That's enough to allow us to learn interesting things. And if we connect a bunch of neurons together, well, if we just connect them like this, it's not enough to learn interesting functions. We can only learn a small set of functions there, not enough to do something like image classification. But if we add one more layer, there's actually a theorem that says now we can learn anything. once we have a network with one hidden layer in the middle and an input and output layer, we can approximate any function. And it's just a matter of learning the right parameters. Actual neural networks tend to have a lot more than just one layer. They tend to have many layers, often hundreds of layers and billions of parameters. But it's only to make the learning easier. Right? The actual ability to represent functions, once we have one hidden layer and those simple neurons that can have a nonlinear function, we can learn anything, at least in theory. So in order to train a model, all we need to do, well, we need to pick some model architecture, pick how the neurons are connected. There's some tricks to learn different model architectures that are better at learning certain kinds of things, like learning to recognize images. And then we just keep guessing until we get something good. Right? And if we've got a good strategy for how to do the guessing, and we've got enough training data, so this assumes we've got training examples with the correct labels, then machine learning is going to work. At least it often does. Right? Often works surprisingly well. OK, so that's the setting that I called supervised learning, where we have training data that has examples of what we want to learn with the intended output. Those are the labels. So is that going to work for training a model like ChatGPT that interacts with language and isn't there to do such a simple thing as sort of tell you what an image is? So the challenge here is, like, we don't have supervised training data. We don't have training data. So this is not a very good joke. Right? I checked that, well, it's maybe better than the joke I would come up with, but it's definitely not something that someone said, here's an input and here's the output you want. Right? So in order to train models like ChatGPT, which are called large language models, we can't rely on having training data that gives us inputs and outputs with the desired labels there. We need to find a lot of data. We need to be able to train from that data without having some sort of manual effort to give all the intended responses. So the way these things work is they're training without needing supervision. And they're training on all of the language that they can find. And the main trick to training them is, well, if you find some language, and this is Wikipedia, there's lots of language on the internet, there's lots of language available other places. You can define the task as, I'm going to mask out one word. So masking out words or tokens or even comments, right? Hide that word and see if you can predict the word. That's a way to sort of automatically get a lot of training data, because now you don't need sort of to manually label training data, but you just take what you find. This is what's called masked language modeling. And it seems in some sense really silly, right? So how are we getting machines that seem so smart if all they're doing is predicting the next word? But to actually predict the next word, well, to do that well, you've got to know a lot, right? You've got to both understand the previous words, what they mean, what they're getting at, but you've also got to understand a lot about the world. You've got to have facts. You've got to be able to do this really well, right? You might need to do things that we would call reasoning. So if you have enough language and you can predict the next word really well, that's going to result in a model that seems to have a lot of intelligence. You need a lot of data for this. So just to give you a sense of how much training data you need, this is a corpus called the pile. It's close to a terabyte of data. It's got all of, where's Wikipedia? So Wikipedia is this size, right? This is all of Wikipedia, right? So this is a lot of text, but it's a small fraction of what's actually used to train models like GPT-4. So the estimate of what's GPT-4 is about this size, about 10 trillion tokens of language just learning to predict the next word. And as you to get that language, well, the internet's not enough. You've got to find language other sources. So the companies that are training these large models have basically done everything they can to get as much language as they can. And they don't worry too much about the quality of the language. It's really just about getting as much as you can to train on. And then the training procedure, pretty similar to what I described, right? With some more tricks to try to make it more efficient. This requires a lot of computation, right? So you may need a few thousand GPUs are what used to be called graphical processing units. They're basically just computing devices that are really good at matrix multiplication. That's the main operation that is needed in training. You need a lot of energy to power that, but not a ridiculous amount. So this is maybe an unrealistic to train GPT-4. People estimate that it was about 60 kilowatt hours, which is the electricity 5 homes in the US use in a year. Kuwait is one of the few places that uses more energy on average than the US, so it's only a couple homes in Kuwait, according to what I could find out. So once you've trained it, what you have, like what you've trained, is about 1 trillion parameters, right? So we saw that first line had 2 parameters. Models that do image classification have a few million parameters. To have a language model, you're talking about billions of parameters, or even up to 1 trillion. So lots of capacity there. And this is what's called a generative pre-trained transformer. That's the big thing, right? And you can download, there are language models that you can download and run on your laptop, right? The program to run it is small. The amount of data that you need to train it is huge, but once you've trained the model, it's something that you can, at least models that are pretty close to as good as ChatGPT, you can run on your laptop. And all they're doing is predicting the next word. If you predict one word, then you can feed that back in and predict the word after that. So you can keep doing that over and over again to generate lots of words. To do better, so if you just train a model to predict the next word, it wouldn't operate like ChatGPT, right? It wouldn't give responses to queries. It wouldn't interact with people the way you want a model to interact with people. So there's another step after you've done what's called the pre-training on the huge corpus of text, which is called fine-tuning. And there, you are actually supervising the model. So you're giving examples where humans are generating high-quality examples of what they want the model to do. Right? And that is expensive, right? You need to hire humans to create these and decide what you want as good examples. Of course, once there's one good model, you can kind of cheat and use that model to train the next model, which companies have been caught doing. It's questions whether this is good. This runs the risk of eventually every model is trained on every other model, and the humans are kind of becoming less relevant. But to do better, you're going to need humans, at least today. And you're also using feedback all the time. So every time someone is using one of these models, they're potentially generating new training data that will be used to improve the model. Because if you're interacting with ChatGPT through the web interface, they can see what you do with the results, right? Whether you ask again, whether you pick something else. So that's a recap of the procedure, right? You need the huge training corpus to train the pre-trained model just by guessing, doing things to try to find the best parameters. Then you need a more expensive but much smaller training process to fine-tune the model for particular tasks. And this ends up working surprisingly well, in some senses amazingly well. So this is doing well on exams students take in the US. This is doing at the silver medal level on International Math Olympiad questions, which are really hard. And doing as well as trained doctors on some medical exams. Right. So looks good, definitely not perfect, and we'll get at that. Okay, so let me pause. See if any questions about that, because now I'm hoping everyone has a basis for understanding what AI is, how large language models and tools like ChatGPT work, and then we'll get into things that you might be afraid of. Yeah, question. Very good question. Okay, let me go back to that graph. And you get a door prize for asking such a good question. Thank you. So like these are different subject exams. There's exams you can see environmental science and art history. And so one good question is, well, is it really understanding these questions and doing well on them because it's intelligent in the way we think of humans being intelligent? Or is it doing well on these questions because it's actually seen them before, right? And that is actually one of the things you can see here. The blue lines were GPT 3.5, which was the original ChatGPT. The green lines are GPT-4. So it looks like it's really improved, right? And in some ways, it probably has. And another question, almost all of the training data for testing, like, so you want the data that you test and you evaluate your models on to be different from the data they were trained on. Because it might just be memorizing things in the training data and repeating them. That's probably not the different, like the reason some AP exams are, well, definitely some AP exams are easier for humans than others, and some are easier for machines than others, right? So there is a difference, and you can see the ones, like this is probably the most striking, like the AP Calculus. GPT 3.5 did horribly on it, but GPT-4 does pretty well, and there are models since GPT-4 that do better, but that's viewed as a harder exam than some of the ones like art history or psychology. These are more about memorizing facts than solving problems. So it's a question of like how much actual reasoning is needed. But even the ones that have reasoning, well, maybe it's doing better on AP Calculus because it's seen, like it's certainly in the training data to have questions from previous exams and maybe from the ones it's being evaluated on. So that's a really hard problem in evaluation, and that's true for the medical test. It's true for the International Math Olympiad to make sure, well, you can use your test on data that didn't exist when the training happened, right? That's one of the things that's done is like there's some cutoff when the model is trained, and then you do the test on data that didn't exist before that. But knowing that it didn't exist before that is actually hard, right? And it may be very similar to things that exist. So there's a lot of work going on to try to evaluate, how well do these models actually do on problems they haven't seen before, and trying to generate benchmarks and data sets where you can synthetically generate new questions. So you know that there are questions that weren't seen, but they're still similar to questions that were seen. So when you decide, is this evidence that the model can actually solve new problems or not? But thank you, yeah. Any other questions? Yeah.
ChatGPT is trained in English and reading and solving. Why in AP literature it didn't get better when it came to like ChatGPT 4? If AP lit is purely just English.
Okay, yeah. So I think maybe there are two parts of it. One is how much of this training data is in English and how much in other languages. And you are right that, let's see, actually I won't go back. You're almost, like a large fraction of the training data is English, right? It is certainly seeing some Arabic, seeing some of many other languages, some languages seeing very little of, but it is dominated by English, which definitely is gonna affect how well the model does on tasks in other languages. And there's, I think, good questions and definitely work going on to say, like, is its reasoning being distorted by, when you try to transfer between other languages, have you learned things in English that sort of transfer but sort of don't and lead to distortions. I think the specific question was about, why it's doing so badly on the English literature. And I don't know enough about what questions are on. It may be part of that exam is actually writing well and graded subjectively by teachers. I don't think they included that in these experiments. I think these are only the multiple choice parts. But there may be questions that are still requiring more understanding and reasoning that it's not as good at answering. But yeah, you'd have to look a little more closely at what's on that exam and how the model did. Okay, so I'm going to transition now to talking about what we should be afraid of, or maybe fear is not the right emotion, but at least concerned about. And break those into sort of two broad categories, right? We could be afraid that the models don't work well enough, but people are relying on them. People trust them in ways they shouldn't. Or we could be afraid that the models work too well. But let me talk about two examples of the model not working. So we talked about like the model is trained just based on predicting next words. Image models are similar. They're trained on sort of seeing images and regenerating those images. But there's no underlying model. So this is one nice example. It looks like a nice artwork if you look a little more closely. So this is the old wise man hugging a unicorn. It does not understand that the unicorn, if the unicorn's horn went through the old man's head, the old man would not be so happy anymore, right? But it looks like a nice artwork until you realize what you're looking at. And the model that generated it, has seen lots of images of unicorns, but it doesn't understand the world, right? And that's true for the language models as well, right? They can generate text that seems very convincing and plausible, that is not based on any reality, because it's just predicting words. The other thing that happens, because it's read all that text, it is exposed to all of the biases and stereotypes that humans have. And in some cases, it actually can amplify them, can make them worse. So these are results from an experiment one of my students did, looking at when a model is predicting from a description of someone's biography their occupation. If the person is female and they're a lawyer, it predicts they're paralegal, right, with a high error rate. So there's a lot of sort of risk that models could be used in ways that perpetuate biases. Here you can see as the name, like English names, some are clearly female, some are clearly male. Other names might be less clear, might have a mix of males and females with that name. And you can see that there's a clear difference as you go along that trend that shows the model having a good understanding of gender associations with names, but also reflecting that in biased outputs. And it can have an impact on sort of an example use of the model to screen resumes and decide who to interview for a job. So those are risks, and those are things that it's important to be aware of. They're risks that can be mitigated, and when people develop and use models can deal with that. And I think that the model's not working. Those are things that, well, we're going to learn, and people are working on, and we're going to find ways to make the models better. So it's important to understand their limitations. But that doesn't seem like something to be fearful of. So we're going to now talk about like fear if the model works too well. And the model could work too well. There are two kinds of fears. There's the fear that someone will use the model in a malicious way, take advantage of the model to do harmful things, right? And I'll give you one example of that. Actually, I'll give you first an example of the model learning too much, right? So the models, and this came up in the question about the AP exams. Well, they're exposed to all this training data. They might just memorize it, right? And they might repeat things in their training data that they shouldn't repeat. They can't be memorizing everything. And the easy way to understand that they're not memorizing everything is that as big as the model is, it's got a lot less information than the size of what it was trained on. So the training data must be bigger. But there could be secrets in the training data, right? It could be, and there certainly are companies training models on your emails or your chat texts. You hope that they're doing that in a careful way that's not going to expose sensitive things in them, but sensitive things could be exposed by a model trained on data that it shouldn't be. It could also generate text that's copyrighted, right? And there's a big lawsuit going on about whether the ChatGPT models, the models trained by OpenAI, are violating copyright for some of the sources they train on, including the New York Times. The other kind of harm is, well, now someone's using an AI tool to do something harmful. Harm is definitely like kind of defined in the eyes of whether something's harmful or good. We think we maybe have some objective notions about, but it's not always that clear, especially for things like surveillance and manipulating people. One quote about this, this is a science fiction writer who talks about the future's already here, it's just not evenly distributed. So to think about that in terms of harm, most of the things that people do with technology or with any tool that are harmful are already being done in some way. And the question is, will AI enable new harms? And by automating things and making them less expensive, well, that's going to expand both the number of victims, potentially, because now the cost of doing the attack is less, as well as the number of people that potentially could carry out an attack. So one example of this, if you know about phishing emails, so people send emails to try to trick the recipients into giving them money or doing something on their behalf. One of the interesting things about these emails, that the initial phishing email is intentionally written to be pretty bad, so only gullible people will respond to it, because there's a lot of human effort after that to try to turn that into money for the scammer, right? But if this could be automated, well, then the whole conversation part could be done by machines in a very cheap way, and you could generate spear phishing emails with much less effort. And so instead of only sort of having manual high-effort spear phishing for high-value targets, you could potentially sort of do it profitably in an automated way to everyone. And there's at least been a demonstration that this could be done. And it is an asymmetric, like most things in security, there's an arms race, right? The tools to protect people from harm can improve and also benefit from the AI technology, as well as the tools for doing the attack. The problem is that attack succeeds if only a few % of the time the message gets through, right? So the arms race is kind of in the favor of the attacker, at least if we play it out this way. So there are lots of potential ways that AI can be used to automate and scale and make attacks less expensive. But I think these are in domains that we already can have good, if we have principled solutions, they will work against the AI automated versions of these attacks as well. Okay, so the other, and this is the most popular sort of science fiction fear, is that AI, we're going to create some AI with the goal of helping humans, and it's going to get out of our control. And there are lots of movies going back to the 1800s, at least stories about this going back to the 1800s. The name robot came from a Czech play that had machines going out of control. Right? So there are lots of science fiction stories like this. There's a more academic philosophical story like this that's about the paperclip maximizing machine. So if you trained a machine to make paper clips and said, you're running a business, your goal is to make as many paperclips as possible, and you did that optimization process that I talked about in the early slides, and you didn't have any constraints and it had access to the whole world, it would say, well, humans are, blood is a really good source of iron. We're going to take, humans aren't useful as paperclips. We're going to take all the blood we can get from humans and turn them into paperclips and take over the whole planet. I don't think that's like something we should really be worried about. Things are not that easy to get out of control. So the main one, and I'm glad when we talked at the beginning, this was the one that several of you raised, is the risk that AI will pose to human value, dignity, and worth. Right? And we're seeing already the start of this, like lots of jobs that are traditional human jobs are getting taken over by machines. Right? And this is not a new trend. This has happened since the Industrial Revolution for hundreds of years, that machines have taken over human jobs. But maybe things are going to be worse with AI. Maybe the kinds of jobs that AI can take over. So for the last part of the talk, I'll try to make some predictions about that hopefully will end up allaying fears rather than making them worse. But we'll see. And my favorite quote about predictions, Paul Gascoigne, a British footballer, said, "I never predict anything, and I never will." So making predictions, hard to keep them. But the most important thing to understand in trying to think about the future, our day-to-day existence, the way we experience the world, the way we tend to think about things is linear, right? We sort of expect if something changes a little bit today, it's going to change a little bit the next day. It's going to change the same amount every day, because that's how it looks to us. But this is actually not true, right? Most things that actually change are not linear. They're changing by multiplying in some exponential way. That it's not changing the same amount, it's changing by some percentage of what it already is, right? And almost everything that changes in the world is actually changing in an exponential way. So this is looking at GDP, sort of wealth creation, very exponential. Any exponential, if you scale it big enough, it looks like completely flat until it finally goes straight up, right? And if you look at other things like books published or crop yields, they all have the same curve. Right? Everything is exponential. And if you were around in 2005, probably if you were around, you were very young then. But in 2005, there were sudden breakthroughs they ran a competition for autonomous vehicles. The first year they ran it, none of the vehicles worked, nothing could go. The second year, the vehicles could finish the whole course, right? And all of a sudden, it seemed like, wow, there's going to be huge progress here. It's on an exponential curve. We'll all be in self-driving vehicles really soon. And I promised an Elon Musk quote earlier. So this was what Elon Musk was saying about 10 years ago, right? In 2016, he said, we'll be able to do a demonstration drive of full autonomy all the way from Los Angeles to New York, all the way across the United States by next year. That was the promise in 2016. If you saw, they did an announcement a few days ago. Now they're promising autonomous vehicles maybe by 2027, right? So it's still more than a year away, right? So this was a reasonable to think if you thought you were on this curve, and that was where you needed to get. If you're actually on this curve, well, it's going to take a lot longer. There definitely has been progress. We're getting closer. So it's hard to predict exponentials, but it's also hard to, it's easy to predict that almost all change will be exponential. It's hard to predict when it will get to the point where things will really change. What is much easier to predict is decreases and increase. So if you look at cost decreases, well, cost decreases only go to zero, right? So anything that we can look at as this would be something we could do if the cost got low enough, well, most things are decreasing in cost in an exponential way. As an example, If you look at communication, if it was 1803 and you needed to send a message across the United States, and this is something Thomas Jefferson, who founded the university that I'm at, wanted to do when he was president, it would have cost about $100 million in today's money to do that. That's what the expedition to send a message across the United States. By 100 years later, it would still cost a lot, right? Sending messages. By the early 1900s, you had telephones, but this was a very expensive. You paid per minute. Yeah, it was very expensive to do, and it was expensive because you needed human operators to connect the call, right? And you needed a lot of infrastructure. But now, since early 2000s, it basically costs nothing, right? We don't think about the cost of communication. But almost everything else is on that curve. So one of the things that we should think about in terms of human dignity and jobs for the future is the cost to automate a job for most jobs is decreasing. What we don't know is how fast, but certainly things like driving, like those costs are, it's still mostly done by humans. Only in very controlled settings do we have fully autonomous driving. And it's going to take time for that cost to come down to be below the human cost. For other occupations, well, the humans might cost less. And the cost to automate, you could automate it, but it's not economical yet. The costs have to go down. There are definitely occupations where the cost might be higher, and certainly we feel somewhat insulated as college professors, but our costs to be automated are going down as well. And this is not a new fear, right? So that's we're in 2024. This was Isaac Asimov writing in 1964, was talking about the main fear for 50 years to the future is there won't be enough work and only a small fraction of people can be involved in creative work. And the worry is about, well, by 2014, we should be in this, society where the most glorious thing you could think of is work. Probably we haven't got there yet. It was a nice prediction. Back in the early 1800s, right? You've probably heard of the Luddites. Like, people use Luddite as a term today for people that are afraid of technology. But that wasn't really what the Luddites were. They were afraid of losing their jobs. They were seeing machines that were making textiles. They were skilled artisans, and they were losing their jobs to these machines, which were actually producing worse quality. And one of the things they really wanted was you couldn't pretend something was human-made when it was made by machines. You had to admit whether it was made by humans or machines. So they were talking about it being fraudulent and deceitful to use machines to produce things that were previously done by humans. So we should think about jobs that won't be replaced by AI. And definitely as students about to finish high school, you might start to be worried about what you're going to do in the future and hope that there will be good things for humans to do. So there's some jobs that will take a long time to be replaced, but they really probably should be. Right? They're going to take a long time to be replaced because there are powerful professions that can prevent them from being replaced. And I think the anesthesiologist in medicine is probably the most clear example of this. There are other jobs that could be done by machines, but humans are cheaper, so it's economical to have humans do them. That's a pretty bleak kind of existence if the humans are just doing things because we're cheaper than machines. So what we really hope that most humans can do is jobs where we care about them being done by humans, right? We care about sports not because some machine couldn't kick harder or run faster or fly, do things that humans couldn't do. We care about it being done by humans. We care about music being done by humans. Right? It's a human experience. We care about humans crafting, which could be food, could be art. So there are lots of things that maybe in some sense machines will be able to do, but we care about them being done by humans. And certainly education is one of those, that there are intrinsically human aspects that the value of having humans do things over machines, even if machines at some level could do them better, it won't be viewed as better. It won't be better at the task. So our hope should be that all humans will have jobs that benefit from being intrinsically human, and it's not a question of competing on cost with machines. And we should be able to get there, right? Technology should be able to automate the tedious things that we don't care about humans doing and leave humans to do the things that we care about humans doing. So I will close with that. I'm happy to take questions as long as you're able to stay and have questions. This is a better machine-generated joke than the first one. So I think Claude 3.5 is a little better, but probably not as good as definitely better than what I could do, but maybe not as good as what a trained comedian or a talented human comedian could do. So thank you. I'm happy to take questions.